Welcome to EPG Pathshala. In today's module, we are going to discuss about hydrometeorology. There are many natural hazards of hydrometeorological origin and mitigation of its effect is very important. So, hydrometeorology is important in understanding, it's a branch of science. So, the understanding of hydrological cycle, water budget and rainfall statistic of storms is very important. It deals with this branch of science also deals with the processes of the hydrological cycle that occur in the atmosphere like evaporation, condensation and precipitation, and in the ground like rainfall interception, infiltration and surface runoff and their interaction. So, in this module we will be seeing what is hydrometeorology and its general importance. We will also see different types of hydrometeors. We will see the distinction between different processes involved in the hydrological cycle. We will analyze, characterize the distribution of rainfall in space and time. We will also see different methods of evapotranspiration measurement as well as the measurement of runoff and stream flow. So, let us start with the hydrometeorology definition. Hydrometeorology is a branch of meteorology and hydrology that studies the transfer of water and energy between the land surface and the lower atmosphere. It is the scientific study of interaction between meteorological and hydrological phenomena, including the occurrence, motion and changes of the state of atmospheric water and land surface and subsurface phases of the hydrologic cycle. Let us see what are hydrometeors. Hydrometeors are any water or ice particles that have formed in the atmosphere or at the earth's surface as a result of condensation or sublimation. Water or ice particles blown from the ground into the atmosphere are also classified as hydrometeors. Some well-known hydrometeors are clouds, fog, rain, snow, hail, dew, rain, glaze, blowing snow and blowing spray. You can see in this table the classification of hydrometeors other than clouds and their symbols as given by the World Meteorological Organization. The classification of clouds we will see in detail in another module. So, in this classification, the meteors are divided into 5 groups: suspended particles, falling particles, that is from precipitation, spout, particles raised by the wind and the deposits of particles. In the suspended particles, it include fog, mist, ice fog. In the falling particles, you can see the rain, supercooled rain, drizzle, supercooled drizzle, snow, snow grains, snow pellets, diamond dust, hail, small hail, ice pellets. In the spout, you can see the tornado, land spout, and in the particles raised by the wind, drifting and blowing snow, drifting snow, blowing snow, spray, snow devil or steam devil. In the deposits of particles, you can see the deposit of fog droplets, dew, dew proper, advection dew, white dew, hoarfrost, hoarfrost proper, advection hoarfrost, rime, soft rime, hard rime, clear ice and glaze. And you can see the corresponding symbols with respect to these meteors. Now, we will see hydrological cycle and its components. The hydrologic cycle is a conceptual model that describes the movement and storage of water above, on and beneath the surface of the earth, that is between the biosphere, atmosphere, cryosphere, lithosphere and hydrosphere. The major components of the hydrologic cycle are evaporation, precipitation, evapotranspiration, interception, infiltration and percolation. Evaporation, it is the change of state from liquid water to vapor. Precipitation, it is all forms of water that reaches the earth's surface from the atmosphere. Evapotranspiration, it is the combined process of movement of water from the earth's surface as evaporation and plant surface as transpiration. It is also termed as consumptive use of water. Interception is the process in which part of the precipitation before falling into the earth's surface caught by vegetation, structure, other surface modifications and evaporated back to atmosphere. The part of the intercepted water by the vegetations which drip off the plant, leaves and joins the ground surface or surface flow is known as through fall. Infiltration. It is the processes in which the water enter into the ground surface. Percolation. It is the deep downward movement of water after saturation of soil. You can see in this figure the hydrological cycle, which includes the estimates of mean water reservoirs. That is the plain font, it is 10 to the power 3 square kilometer, and of the flow of moisture between the stores, that is in the units 10 to the power 3 kilometer square per year. And the component of the hydrological cycle includes the processes like evaporation, transpiration, condensation, precipitation, interception, deposition, runoff, that is surface runoff, interflow and base flow, infiltration and percolation, sublimation, melting and groundwater flow, depression storage and moisture storage in the unsaturated zone of soil. For the ease of describing the cycle, the evaporation from the ocean through absorption of solar radiation can be considered as the starting point. Of the total evaporated water, about 91% is returned to the ocean by means of precipitation, whereas remaining 9% is transported to areas over the land masses where atmospheric or climatological factors induce the formation of precipitation. A part of precipitation may evaporate back to atmosphere while falling. Another part may be intercepted by vegetations or any surface structure, and the intercepted water either evaporated back to atmosphere or fall to the earth's surface. A part of the water that falls on the earth's surface infiltrate into the soil, thereby increasing the soil moisture content and further percolate down to become the part of the groundwater. The water stored in the soil is transpired back to the atmosphere by the vegetation, and the part of water that reaches the streams or channels by means of surface flow, which is known as runoff. Now we will see the rainfall analysis and characterization. For this, the first one is mass curve. This is the graphical representation of cumulative rainfall over a period of time, which is plotted in a chronological order. From this, the useful information like magnitude and duration of rainfall can be obtained. The intensity of rainfall at various time intervals for a given storm event can be obtained from slope of the curve. Hydrograph. This is the graphical representation of rainfall intensity and time. The hydrograph is derived from the mass curve and represented as bar chart. The hydrograph is required for the development of a designed storms to predict extreme floods. The area under a hydrograph represents the total precipitation received in that period. The third one is the missing rainfall data estimation. It is by means of simple arithmetic method, normal ratio method, modified normal ratio method, inverse and inverse distance method. For n stations, that is 1, 2, 3 up to n, the annual precipitation values are P1, P2, P3 up to Pn respectively. Px is the missing annual precipitation at station x, which is not included in the above n stations. And the normal annual precipitation N1, N2, N3 up to Ni at each of the above n plus 1 stations including the station x is known. So, normals for a particular day, month or year is calculated over a specified 30-year period, and it is mainly by simple arithmetic average. Here in this method, the missing precipitation Px can be determined using simple arithmetic average if the normal annual precipitation at various stations are within 10% of the normal precipitation at station x. As per this simple arithmetic method, Px is equal to P1 plus P2 plus P3 plus etc. plus Pn divided by n. Next is the normal ratio method. If the normal precipitation vary considerably, then Px is estimated by weighting the precipitation at various stations by the ratio of normal annual precipitation. And the normal ratio method gives Px is equal to nx by n of multiplied by P1 by N1 plus P2 by N2 plus up to Pn by Nn. This method is based selecting n, which is usually 3 stations that are near and approximately evenly spaced around the station within the missing record. And the third method is by modified normal ratio method. Normal ratio method is modified to incorporate the effect of distance in the estimation of missing rainfall. Here, the gamma x is equal to sigma I is equal to 1 to n di 1 by b rx bar by r1 bar. Rx is equal to sigma I is equal to 1 n di 1 by B, Rx bar by Rz bar of Ri divided by sigma I is equal to 1 up to n di 1 by B, where gamma x is the normal rainfall, d is the distance between the index station I and the gauge station with the missing data or ungauged station, n is the number of index station, and b is the constant by which the distance is weighted. Normally 1.5 to 2 is used, commonly used, d is 0.5. The fourth method is the inverse distance method. This method is considered as the most accurate one in comparison to the other methods. Here the amount of rainfall is estimated at a location. It is a function of rainfall measured at the surrounding stations and the distance to each station from the ungauged location. Rainfall gamma x at station x is given by Rx is equal to sigma I is equal to 1 n Ri by d zb divided by sigma I is equal to 1 n multiplied by 1 by dzb, where b is commonly used, b is equal to 2 is commonly used. As in the inverse distance method, the weighting is strictly based on the distance, hence this method is not satisfactory for the hills regions. The normal precipitation, it is the average value of precipitation at a particular date, month or year over a specified 30-year period. Thus, the term normal annual precipitation at any station is the average annual precipitation at that station based on a specified 30 years of record. The frequency analysis of rainfall over a location. The first step in designing the engineering projects dealing with flood control, gully control, etc. is to determine the probability of occurrence of a particular extreme rainfall. The frequency analysis deals with the chance of occurrence of an event over a specified period of time. Suppose P is the probability of occurrence of a rainfall event whose magnitude is equal to or in excess of a specified magnitude x. The recurrence interval, which is also known as return period, is related to P. T is equal to 1 by P. There are two methods for performing frequency analysis. One is empirical method and the other one is analytical method. The exceedance probability of the event is obtained by the use of empirical formula, which is known as plotting position. The Weibull formula is the most commonly used plotting position formula. In this method, first P and T are calculated for all the events in the series, and then the variation of rainfall magnitude is plotted against the corresponding T on semi-log or log-log paper. The rainfall magnitude for any recurrence interval can be determined by extrapolating the plot between magnitude and recurrence interval. Empirical procedures can give good results for small extrapolations, but the error increases with amount of extrapolation. So for more accurate results, analytical methods using frequency factor are used. The spatial measurement of rainfall. Generally, we measure precipitation at a single point, which always not the representative of the amount of waterfall over the entire area. As hydrological analysis requires information on the precipitation over a defined area, a network of point measurement is required. The network of precipitation measurement points can be converted to average value over the area by using arithmetic mean method, Thiessen polygon method, isohythal method. Arithmetic mean method. In this method, the arithmetic mean of the precipitation for all the stations within the area is computed. Since this method assigns equal weight to all the stations irrespective of their relative location and other factors, it should be used in area where rainfall is uniformly distributed. If P1, P2, P3, Pi, Pn are rainfall values in a given period in n stations within the defined area, then mean precipitation over the area can be calculated as P bar is equal to P1 plus P2 plus P3 plus dash dash plus Pi plus dash dash Pn divided by n, which is equal to 1 by n sigma I is equal to 1 to n Pi. And the second method is the Thiessen polygon method. This is a graphical method in which rainfall recorded at each station is given a weightage based on the relative areas of each measurement stations in the Thiessen polygon network. The individual weights are multiplied by the station observation and the values are summed to obtain the average precipitation. This method is useful for areas which are more or less plain and are of intermediate size, that is from 500 to 5000 square kilometer. This method is also used when there are few rain gauge stations compared to size. The area of each polygon AI is determined and average precipitation is calculated. Here the equation is P bar is equal to P1A1 plus P2A2 plus P3A3 plus dash 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 plus PIAI plus dash dash plus PNAN divided by A1 plus A2 plus A3 plus dash dash plus AN, which is equal to sigma I is equal to 1 N PIAI by A, where A is the total area. The next method is the isohethal method. This is a graphical technique which involves drawing estimated lines of equal depth of rainfall over an area based on point measurements. Then multiply the area between each contour by the average precipitation in the area to get the rainfall volume in that area. Sum these volumes to get the total rainfall volume and then divide the total rainfall volume by the area of the watershed to get the average precipitation in the watershed. Next one is the evapotranspiration. Evaporation. Factors that affect evaporation are wind, temperature, heat, exposed surface area, humidity, nature of the liquid and vapor pressure. Evaporation is estimated by using evaporimeters, empirical equations and analytical methods. Evaporimeters are used for measuring evaporation. It consists of water containing pan which are exposed to atmosphere and the loss of water by evaporation is measured at regular interval. The most commonly used evaporimeters are USWB class A pan evaporimeter, pitch evaporimeter or atmometer and sunken evaporation pan. Transpiration. It is the process in which the liquid water contained in the plant tissues removed to the atmosphere as the vapor. The crop loses their water through stomata. The transpiration of plants also depends on the energy supply, vapor pressure gradient and wind, soil water content, water logging, soil water salinity, ability of the soil to conduct water to the roots, crop root and foliage characteristics and cultivation practices. Evapotranspiration. As evaporation and transpiration occur simultaneously, it is difficult to distinguish between these two processes. Thus, in the hydrology and in irrigation practices, both these processes are considered as a single one, that is known as evapotranspiration. Evapotranspiration mostly influenced by the availability of water for a given set of atmospheric conditions. When sufficient moisture is available to meet the needs of vegetation fully covering the area, the resulting evapotranspiration is called potential evapotranspiration. Measurement of evapotranspiration. The direct measurement of evapotranspiration can be done in 4 ways. Lysimeter technique, field experimental plot study, soil moisture depletion studies and water balance study. Among these, lysimeter is most accurate one. What is a lysimeter? A lysimeter is a special water-tight tank containing a block of soil and set in a field of growing plants. The plants growing in the lysimeter are the same as in the surrounding field. Evapotranspiration is estimated in terms of the amount of water required to maintain constant moisture condition within the tank measured either volumetrically or gravimetrically through an arrangement made in the lysimeter. Lysimeter should be designed to accurately reproduce the soil conditions, moisture content, type and size of the vegetation of the surrounding area. They should be so buried that the soil is at the same level inside and outside the container. You can see in this figure the schematic diagram of a weighing lysimeter. Estimation of evapotranspiration. The difficulty in direct measurement of evapotranspiration under field condition resulted in the use of different methods for estimation or prediction of evapotranspiration on the basis of climatological data. And the most commonly used empirical formula are Blaney-Criddle method, Thornton method, Hargreaves method, FAO-Penman-Monteith method. And this FAO-Penman-Monteith method is considered as the standard and widely used method. FAO-Penman-Monteith method. It is used to estimate reference evapotranspiration. And the equation for calculating the evapotranspiration is ET0 is equal to 0.408 delta Rn minus G plus gamma 900 divided by T plus 273 U2 ES minus EA divided by delta plus gamma 1 plus 0.34 U2. Here ET0 is the reference evapotranspiration and the unit is millimeter per day. And Rn is the net radiation at the crop surface in megajoule per square meter per day. T is the mean daily air temperature at 2 meter height in degrees Celsius. And U2 is the wind speed at 2 meter height in meter per second. And ES is the saturation evaporation in kilopascal. EA is the actual vapor pressure in kilopascal. ES minus EA gives the saturation vapor pressure deficient, that is also in kilopascal, and delta is the slope of vapor pressure curve, that is in kilopascal per degree Celsius, and gamma is the psychometric constant, which is in kilopascal degree Celsius, kilopascal per degree Celsius. The measurement of runoff. The RCCS runoff curve number method is developed by the United States Department of Agriculture, that is USDA NRCS. NRCS denotes Natural Resources Conservation Service. The runoff curve number is based on the area's hydrologic soil group, land use, treatment and hydrologic condition. And the runoff equation is Q is equal to P minus IA all square divided by P minus IA plus S, where Q is runoff in inch and P is rainfall in inch. S is the potential maximum retention after runoff begins in inch, and IA is the initial abstraction in inch. Initial abstraction IA is all the losses before runoff begins. It includes water retained in surface depressions, water intercepted by the vegetation, evaporation and infiltration. IA is highly variable but generally is correlated with the soil and cover parameter. It is approximated by IA is equal to 0.2 S. So, by replacing IA, the equation can be rewritten as Q is equal to P minus 0.2 S all squared divided by P plus 0.8 S. S is related to the soil and cover conditions of the watershed through the curve number Cn. And this Cn has a range of 0 to 100 and S is related to Cn by S is equal to 1000 by Cn minus 10. The NRCS curve number is related to the soil type, soil infiltration capability, land use and depth of the seasonal high water table. To account for different soils' ability to infiltrate, NRCS has divided soil into 4 hydrologic soil groups, that is SHGs, hydrologic soil groups, which are SHG group A, group B, group C and group D. HSG group A denotes the low runoff potential. These are the soils with high infiltration rates even when thoroughly wetted. The examples are deep well-drained sands and gravel. And the final infiltration rate often exceeds 7.6 millimeter per hour. The second group is SHG group B, that is hydrologic soil group B. Soils with moderate infiltration rate when thoroughly wetted. The examples are moderately deep to deep, moderately well-drained to well-drained, with moderately fine to moderately coarse texture. And the final infiltration rate in this group of soil ranges between 3.8 and 7.6 millimeter per hour. In the third group, that is HSG group C, it has slow infiltration rates when thoroughly wetted, and it mainly consists of soils with a layer that impedes downward movement of the water or soil with moderately fine to fine textures. And here the final infiltration rates are between 1.3 and 3.8 millimeter per hour. And the fourth group is the SHG group D, which has high runoff potential, and they have very slow infiltration rate when thoroughly wetted. And examples are clay soil with high swelling potential, soils with a permanent high water table, soils with a clay pan or clay layer at or near the surface, and shallow soils over nearly impervious materials. And it has a final infiltration rate in these soils is less than 1.3 millimeter per hour. And how to measure the stream flow? Stream flow is measured at gauging stations. Stream flow is unique among water cycle components in that it both spatially and temporally integrates surplus runoff and water upstreams within a catchment basin. And the measurements are made by determining the discharge in each subsection of a channel cross section and summing the subsection discharges to obtain a total stream flow discharge. You can see in this figure the conventional methods and the advanced techniques for the discharge measurement. Under conventional method, it is divided into direct and indirect methods. The direct methods include velocity area methods using the current meter, velocity area methods by using the floats and by dilution methods. And in the indirect method, it's by slope area method, by stage discharge relations and by the measurement by hydraulic structures. In advanced techniques for the discharge measurements are moving bot method, ultrasonic or acoustic method and the electromagnetic method. So to conclude, hydrometeorology is a branch of meteorology and hydrology that studies the transfer of water and energy between the land surface and the lower atmosphere. Hydrometeors like clouds, fog, rain, snow, hail, dew, rain, glaze, blowing snow and blowing spray are any water or ice particles that forms in the atmosphere or at the earth's surface as a result of condensation or sublimation. We have seen the WMO classification and the symbols given by them for the different hydrometeors. Hydrological cycle is the study of water movement between the atmosphere, water bodies and the earth. And the major components of this hydrological cycle are precipitation, evaporation, transpiration, interception, infiltration and percolation. And we have seen the rainfall analysis and characterization by the mass curve method, hydrograph, depth area relation and missing rainfall data estimation. Thiessen polygon method is also applicable when there are few rain gauge stations compared to size of the area. We have seen the curve number method, which is most accurate for the estimation of runoff from the rainfall. So we have seen different measurements for the evaporation, transpiration, runoff and the stream flow. Thank you.